All right, y'all, we're prepping for the exam this week. And as promised, I'm gonna do a review for the next couple of lectures for the exam. And today I'm gonna go over two problems from each section in chapter 6. So 6.1 to 6.4, and I've hand selected a couple problems from each section. I can't, of course, cover everything. That's what the other lectures are for, and the homework and everything else. But I thought I would throw y'all some extra examples just to jog your memory. All right, so we're starting with 6.1. And remember, chapter 6 is all about probability, right? So we are dealing with the mathematics of probability, which was using quite a bit of what we learned in chapter 5, dealing with set theory. So we have to remember everything that we learned in chapter 5, basically, to navigate chapter 6. All right. So this first problem, this is number 6 from the back of the book, says an experiment consists of tossing a coin 4 times and observing the number of heads and tails, the sequence of heads and tails. The first question is, what is the sample space for the experiment? All right. So this is a case where we need to list all of the possibilities. The sample space consists of all possible outcomes. So it's a set, and each item in the set will have 4 entries. So we can represent each outcome as a kind of like a coordinate pair, but just 4 coordinates. So for instance, we could start by saying, let's consider all the possibilities where we flip a heads first. So we start with the heads. We could have heads and 3 tails. We could have a heads, and then 2 tails. We could have a heads, and a tails. Or we could have a heads, and a heads. Okay. So that's 4 of the possibilities. We should know that there's 16 in total, because there are 2 options per toss, and there are 4 tosses. So that's 2 to the 4th power, which is 16. So we've listed 4 of the possibilities. We could play the same game and say, what happens if we start with the tails? We could have a tails and 3 heads. 2 tails, then 2 heads. 3 tails and heads, or all 4 tails. Okay. So that means we're halfway through this. So now we have to get into a different way of thinking about this. So we could say, what are all the possibilities when we have a heads then a tails? So say heads, tails, then we could have 2 heads, tails. We could have another heads, tails, tails. We could have 2 tails, but we've already listed that option. So we could have tails, heads. So we're getting there. You'd have to continue listing out all the examples, all the possibilities. You can see that this is actually kind of tough to do it this way, because you're not quite sure if you have exhausted all the possibilities. So one of the reasons I wanted to start doing it this way is a cautionary tale. This is how some people might approach it, but you're going to quickly see that it's hard to tell if you've done everything, exhausted all the possibilities. So the best way to do a problem like this actually is to use a tree. Okay, so start by saying, okay, you have 2 options on the first flip, a heads and a tails. Then on the second flip, you have two options. Then on each flip from there, you have two more options. And then that's 1, 2, 3 flips. So we have one more flip. Running out of space here. Make sure you leave enough space for your trees. Okay. So now to list all the options, you just need to consider all the paths through the tree. So for instance, this is your starting point. You could go up this leg and that'd give you 4 heads. And once you do that, you can, one way I suppose we could do that is we could circle that option. So we've gone through that. Now instead we go heads, then tails, then heads. You can see how you might do this. Heads. That's one option. You could go heads first, then another heads, then a tails and a heads. That gives you another option. 2 heads, a tails, and a heads. And so this is really one way you can sort of graphically think your way through this problem is using this tree. Consider every possible path through the tree. And you'll kind of start seeing how what the options are. You can go up to, you go up 1 heads, then take a tails. You can go up 2 heads and take a tails, go up 3 heads, take a tails, go up 4 heads. So in terms of going up this path, we've just about exhausted all the possibilities. We can go up 2 heads, a tails, and a tails. So that would be another possibility. 2 heads, a tails, and a tails. And we can go up 1 heads, a tails, and then we have, sorry, here, we should do this one, heads, tails, tails. Yes, heads, tails, tails. Heads, tails, we did that one, heads, tails. Yep, so you can see how we've gone through all the iterations on that branch. We can do heads, tails, heads, or heads, tails, tails. Can sometimes be useful to use colors here to help you. Make sure you haven't missed any of the possibilities, but you have to kind of consider all the paths through the tree. And at that point, we can see that there's nothing that hasn't been circled up on this top branch. So we've considered all the possibilities of starting with the heads here. And we should 1, 2, 3, 4, 5, 6, 7, 8 have half of the possibilities. So here's 8 out of the 16 possibilities. So you would just play the same game with the bottom half of this tree and write out all the possibilities. So I'm going to assume that you are capable of that. Okay, so once you do that, you can list it, and that would constitute the sample space. All right, now we want to calculate the probability that the probability of event 1. So, or sorry, no, we're not doing probabilities yet. So here we're just listing what the event is. Okay, so remember that an event is a subset of the sample space. So here they're interested in all those simple events where there are more heads than tails. More heads than tails. So that means there must be at least 3 heads. So you consider all the ways of having 3 heads. You can have 3 heads right out the bat. And you can consider all the scramblings of that. So a heads, tails, then a heads, tails, heads, tails, heads, heads. And that should be all the ways that we can have 3 heads and 1 tail. And then of course there is one last option, which is all heads. Because we definitely have more heads than tails if we flip all heads. Okay, so that would be event 1. Event 2 says first toss is a heads. So that's the only thing that we need. First toss is a heads. So start with the heads and consider all the possibilities. So one thing that's worth doing is think about the what the total number should be. So once we fix the first entry as a heads, we have 3 options to fill, and each of those has 2 possibilities. So that's 2 times 2 times 2, which is 8. So we should end up with 8 outcomes here. So first toss is a heads. We could have all heads. We could have 3 heads and a tails. We could have 2 heads and 2 tails. We can have 1 heads and 3 tails. And then you have to consider the various scramblings of these 3 options here. So this is an option with 1 tails. This is an option with 2 tails. This is an option with 3 tails. So how can we scramble this so that there's always a heads in front? So we know we can't scramble the 4 heads because every scrambling of 4 heads is still 4 heads. And we can't scramble the last entry, heads with 3 tails, because we have to fix the first heads, and any scrambling of 3 tails is still just 3 tails. So the only other things that we can scramble are these 2 in the middle. So how many ways are there to have 1 tails with the heads in the first entry? So it could be heads, tails, heads, or heads, tails, heads. So those are all the scramblings of this second one where we only have 1 tails. And then you have to consider, how can you scramble the second one where we have 2 tails and 1 heads? So didn't give myself a lot of space here. So we can have a heads, tails, say heads, tails, tails. That's 1 scrambling. Fix the first heads, then we could have a tails, and a head. And I think that's it. That should give us our 8. 1, 2, 3, 4, 5, 6, 7, 8. Done. So again, it's really useful to know what the total number ought to be so that you don't sit there scratching your head for a long time trying to come up with some final option when there really is none. So I knew that there should be 8. I did all the scramblings that seemed to make sense and came up with 8. So that would be our event 2, where the first entry must be a heads. All right. So finally, it asks us for the intersection of the two events, event 1 intersect event 2. So what did they have in common? So if you look at your event 1, that's really the one to look at. Here, you just need to choose those options that have a heads in the first slot, because those are the only ones that will show up in the intersection with E2. So E1 intersect E2 is going to have heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads, and 4 heads, which we have in both events. All right. So a lot of listing of options here. This is more tedium than it is a challenge. It's just tedious, but you do need to be careful. The best word of advice I have for you is try to think about what the total number of outcomes ought to be, so that at least gives you a target to shoot for. All right. All right, we're still in section 6.1. Looking at number 11. Here you've been given the sample space and 3 events within the sample space, and we're asked, are the events E and F and G mutually exclusive? Mutually exclusive. So remember what it means to be mutually exclusive. That means that the intersection of any of the 2 events in question is empty. So if we look at E intersect F, E consists of 1, 2, F consists of 2, 3. So the intersection has 2, which is not empty. Therefore, E and F are not mutually exclusive. Now we look at F and G. F is 2 and 3, G is 1, 5, 6. So it's simple to observe that their intersection will be empty. If their intersection is empty, then we can say F and G are mutually exclusive. Okay. All right, moving on to 6.2. 6.2, we're actually starting to assign probabilities to all these events. So in 6.1, we covered how to write down a sample space and various events, which are subsets of the sample space. Now we're going to assign probabilities. So here we're told a box contains 7 slips of paper. 1 slip of paper has an A printed on it. 1 slip of paper has a B printed on it. 3 have a C, and 2 have a D. We want to determine the probability distribution for the experiment where we're drawing 1 slip of paper and observing the letter. So when you're asked to develop a probability distribution, you should think table. You're going to make a table with the outcomes and the probabilities. So the various outcomes, are get an A, get a B, get a C, get a D. Probabilities are relative frequencies. So what we do is we figure out how many ways are there to get an A versus how many ways are there to get any result. So there's 1 A in the box, and there are 7 slips of paper total. So the probability of getting an A is 1 out of 7. Similarly with the B, there's 1 B out of 7. There are 3 C's out of 7 and 2 D's out of 7. So remember the properties of a probability distribution are that the individual probabilities should always be positive and less than 1. And if we add up all the individual probabilities for the distribution, it should add up to 1. So we have 1/7 plus 1/7 plus 3/7 plus 2/7. That's 7/7, which is 1. So this is a viable probability distribution, and we're good to go. All right. So now we're going to look at number 20. Here, trying to get this all, here we go. You are given a probability distribution and a couple events in this sample space. So the event S1, S2, E, which is S1, S2, and the event F, S3, S5, S6. And we're going to be asked to find various probabilities. Okay. So part A, let's find the probability of E and find the probability of F. So the observation to make here is that E, which is S1, S2, is equivalent to S1 union S2. So we're finding the probability of E, we're finding the probability of that union, and we're going to assume that without any further information that all of these events are mutually exclusive. So the probability of E is the probability of S1 union S2, which is just the probability of S1 plus the probability of S2. And this we read off our probability distribution. So that's 0.25 for S1 and, oh, sorry, that's S2. 0.05 for S1 and 0.25 for S2. And so those sum to 0.30. I'm going to put a line here. All right. Probability of F, we think of this the same way. F is S3 union S5 union S6. So the probability of F will just be the probability of S3 plus the probability of S5 plus the probability of S6. S3 is 0.05, S5 is 0.63, and S6 is 0.01. So those should sum to 0.69. Okay. All right, now we're going to find the probability of E complement for part B. So who is E complement? E complement is everything that is not in E. E consists of S1, S2. So E complement consists of S3, S4, S5, S6. So this will be the probability of all of those added together. S3 plus S4 plus S5 plus S6. So that's everything that's outside of E. So we add up all those numbers. That's 0.05 plus 0.01 plus 0.63 plus 0.01. And what are we going to have? This looks like 0.70. All right. Now we're going to look at the probability of E intersect F. All right, looking at E and F, E has S1, S2, F has S3, S5, S6. So when we intersect the two, they are empty. The intersection is empty. So this is something that a lot of you kind of got a little confused about. So the sets are empty, or the set E intersect F is empty, which implies that the probability of E intersect F is 0. Okay, so the sets are empty, therefore the probability is 0. You never want to say the probability is empty. That doesn't make sense. All right, then E union F, that is S1, S2, S3, S5, S6, all put together. So everything excluding S4. So really, I can think of this, since we're a little bit more familiar with probability now, this is 1 minus the complement of E union F. So, and that complement, everything that's outside of E union F is just S4. So that's 1 minus the probability of S4. And that's 0.01. So this must be 0.99. All right. So that is, those are the two problems I wanted to go over for section 6.2. Now let's take a look at section 6.3. All right, first problem we're looking at is number 4 from 6.3. Here we're told that an urn contains 7 green balls and 5 white balls. A sample of 3 balls is selected at random. We want to find first the probability of only green balls are selected. Okay, so the way to think about this is we have some event, and to compute its probability, we're going to find the number of ways of achieving that event or getting that certain outcome over the total number of objects in our sample space. So this is the formula that we'd be using here. So for this probability, only green balls, I'm just going to call it E. The number of ways of getting only green balls. If we're selecting 3 balls at random from this urn, and it contains 7 green balls and 5 white balls, that means it contains 12 balls in total. So the way to think this through is first, what are the total possible ways of selecting 3 balls out of this urn? Well, there are, upon the first choice, there are 12 options. Then the second choice, we have 11 options. Then the third choice, we have 10 options. So the total number of objects in the sample space is 12 times 11 times 10. How many ways are there to select 3 green balls? Well, when we select the first green ball, there are 7 balls to choose from. 7 green balls. When we choose the second, there are 6. And when we choose the third, there are 5. So the total number of ways of choosing 3 green balls is 7 times 6 times 5. So we create a ratio out of those two. And we can do this any number of ways. You can just punch it into your calculator, or you can do some simplification, like 6 and 12 turn into a 2, 5 and 10 turns into another 2. So this ends up being 7 over 22, which is irreducible. So that is our probability. So it's all about figuring out the number of ways of selecting 3 green balls versus the total number of ways of selecting any 3 balls. All right. Part B, we're asked, what is the probability of selecting at least 1 white ball? So we can select more than 1 white ball, but we know that we must select at least 1 white ball. Okay. I'll call this the event W, the probability of W. We're going to approach this the same way. What are the total number of ways of selecting 3 balls? That's 12 times 11 times 10. What are the total number of ways of selecting at least 1 white ball? Okay, so this one we need to be careful. Now, we don't care about the order here. We don't care whether we select the white ball first or we select it third. It doesn't matter. So order doesn't matter. All we care about are unique combinations. So the way I think this through is, let's just say that the first selection must be a white ball. So when we select that first ball, it's already fixed. There is no option. So there is only one way to select that white ball. I know that seems a little confusing, but we're fixing that outcome. There can be no other way. So there's one option for the first selection, and then when we select the next two, we don't care about the colors. So we've pulled one ball out. So then there's 11 left to choose from for the second selection, and then 10 to choose from for the third. So the way to think about this one, again, is to say you're not allowing for any randomness there. There is only one outcome, which is you're getting a white ball for that first selection. The next two, you're allowed to have 11. You have 11 options because you've pulled a white ball out. So now there's 11 balls left. So there's 11 options for the second selection, and then 10 for the third, since we've again removed one more ball. So we can see what happens here pretty easily with the math. 11s cancel, 10s cancel, and we get 1/12. So 1 out of 12 ways of having one white ball out of the 3. Okay. I think some of these, what we call combinatorics, the sort of mathematics behind figuring out combinations and permutations, this is where a lot of you struggle. And so you really want to, if anything, focus on section 6.3, because you use a lot of this math that we covered in chapter 5 to do these probability problems. And so this second problem that I've chosen, number 41, is a good example. This is a tricky problem, and I chose it for that reason. So I guess pay close attention to how we're going to do this. So we're told that a man, a woman, and 3 children, so let's just say a husband, a wife, and their 3 kids, line up for a picture. What is the probability that they line up in such a way that the parents will stand next to each other? We want to figure out this probability. In terms of the formula, we're going to use the same formula we used before. What are the number of ways that we can line these people up versus the total number of ways? What are the number of ways that they can line up so that the parents are next to each other versus the total number of ways that they can line up? Okay, so we're going to call this event E again, just because it's simple. And then we're going to have to do some hard thinking here. So the first thing to figure out, the easiest thing to figure out, is what are the total number of ways that these 5 people can line up. Now here we're actually concerned with order. Order matters. Is it, mom, then dad, then oldest brother, youngest brother, daughter, right? Each individual has each person is distinguishable from the other person. So order matters in this case. Whereas with the colored balls in the urn, we can't distinguish between any one of the 5 white balls. So there's no distinction. We can't tell if it's the 5th ball or the 4th ball or the third, But here we have a clear distinction between the 5 objects in question. So we do have to consider permutations as opposed to combinations here, because order matters. So how many ways are there for these 5 distinguishable objects, the mom, dad, kid 1, kid 2, kid 3, to line up? Well, there's 5 options, and the first place has 5 options, then 4, then 3, then 2, then 1. So this is a 5 factorial. All right, that's the easy part. Now for the hard part. How many ways are there for the 5 individuals to line up so that the mom and the dad end up next to each other, and how to think through this problem? So the way that I thought through it that helped me is I consider mom, dad, and then I'm going to say kid 1, kid 2, kid 3. Okay, so there are 5 people here, but because we are interested in how they can line up in such a way that the mom and the dad are always next to each other, what we're going to do is consider mom and dad as one object. So that's going to be one way to help us out here. All right, so how many ways first are there? How many different orderings are there for mom and dad? Well, it can either go mom, dad, or dad, mom. So there are 2 possibilities there. Technically, we would say it's 2 factorial ways of reordering mom and dad, which we know is equal to 2. Okay. How many ways are there to order the kid 1, kid 2, kid 3? That's 3 factorial. So far, with these 2 numbers, what we figured out is there are 2 ways to reorder mom and dad, and there are 6 ways, 3 factorial, 6 ways of ordering the kids. Now, the way I've written it, this is only one possibility, where you have mom, dad, then 3 kids. But you have to consider that you could have kid 1, then mom, dad, then kid 2, kid 3, or kid 1, kid 2, then mom, dad, then kid 3, or kid 1, kid 2, kid 3, then mom, dad on the end. So if you think about these as 4 objects for this particular sequence, you can reorder it 4 different ways. So you could either have mom, dad, 1, 2, 3, or 1, mom, dad, 2, 3, or 1, 2, mom, dad, 3, or 1, 2, 3, mom, dad. So that's 4 ways of reordering each possible sequence. So these 2 factorial times 3 factorial are the number of sequences without order considered. And then there are 4 ways of reordering each given sequence. So 4 ways of reordering it. So once you've established this mom, dad, 1, 2, 3, then you can switch them around 4 different ways. So the total number of ways of having mom and dad next to each other in the picture is 2 factorial times 3 factorial times 4. 4 again coming from the idea that we regroup these objects so that the mom, dad is sort of considered as a unit. And then how can we reorder them? So we got some math to do here, but it simplifies pretty easily. The 4's cancel out. 3 factorial is 3 times 2 times 1. So that cancels out with these 3 here. And all you're left with is 2 factorial over 5, which is 2 over 5. So that is a tough one. You got to think about it the right way. And there may be another way of thinking about it that is more clear to you, but that's what worked for me. All right. So finally, we're going to look at section 6.4. So here we're dealing with conditional probability. All right, so we're going to look at number 3 first. Here we're told we have some sample space S and 2 events E and F, which are, again, subsets of S. We're told that the probability of E is 0.5, the probability of F is 0.4, and the probability of E intersect F is 0.1. We're going to be asked to compute all these probabilities. So what is the probability of E given F? So the thing to remember here is the formula. So that's the probability of E intersect F over the probability of F. These are all values that we've been given. So E intersect F was 0.1, F was 0.4. So that should give us 0.1. 0.25. Similar formula here for F given E. So the probability of F given E. So that's still the probability of F intersect E, but remember the given is the one that goes in the denominator. So that's a probability of E in the denominator, whereas F was the given in the first problem. Now E is the given, so it goes in the denominator. So that's going to be 0.1 still, because F intersect E is the same as E intersect F. But then the probability of E is 0.5. So that should give us 0.2. All right. Next, they're asking us for the probability of E given F complement. All right, so if we're using our formula, that's the probability of E intersect F complement over the probability of F complement. So how to think about this? Well, in both these cases, we can think about the complement rule. So it's easy to see how we'd use it down here. The probability of F complement is the same as 1 minus the probability of F. Here, the probability of E intersect F complement is the same as the probability 1 minus the probability of E intersect F. So that one might not be as obvious to you. So now we have now we can use the values that have been given. So that's 1 minus the probability of E intersect F, which was 0.1, over the 1 minus the probability of F, which was 0.4. So that's 0.99, no, 0.9 over 0.6. Hold on a second, doing this wrong. Huh. Right, so this shouldn't be a 1 here. That's where this should be the probability of E. So let me spend some time explaining that once I do the math here. So this shouldn't be 1, this should be the probability of E. So that's 0.5, not 1. And then 0.5 minus 0.1 is 0.4. So that gives us 2/3. Okay, so let me explain what's going on here before I move on. So we're being asked for the probability of E intersect F complement. And I said that that was equivalent to the probability of E minus the probability of E intersect F. So how does that make sense? Let's see if it does make sense. So here's E, here's F. And here's E intersect F. Okay, so the probability of E intersect F complement, that's what we're looking for. Well, that's everything that's that's in E that's outside of F. So if we look at this Venn diagram, that actually is this little crescent moon right here. That's E intersect F complement. So you can see that that shaded area is equivalent to the E minus E intersect F. We take away E intersect F, and we're left with E intersect F complement. So that's how these probabilities work out. Probability of E intersect F complement is probability of E minus probability of E intersect F. So study that Venn diagram and it'll make sense to you. Okay, so for part C, we got the result 2/3 or 0.66. Finally, we're asked for the probability of E complement given F complement. So that would be the probability of E complement intersect F complement over the probability of F complement. Okay, so how do we think our way through this? We know how to deal with the F complement. That's just 1 minus probability of F. But how do we deal with this thing? The E complement intersect F complement. What is that? So let's look at it in terms of a Venn diagram. Here's E, here's F. And we're asked to find, we're looking for the probability of, sorry, E complement intersect F complement. So everything that's outside of E and everything that's outside of F intersected. So there's our sample space. So outside of E and outside of F. So E and F, everything that's outside of E and F. So that's everything here. Which we know from De Morgan's laws is the same as E union F complement. So we can see that here's E union F and everything outside of E union F. Okay, so this should be the same as 1 minus the probability of E union F. Great, but they never told us what the probability of E union F is. So how can we possibly find this probability? Well, we use the inclusion-exclusion principle. So remember what that says. It says the probability of the union is the probability of one plus the probability of the other minus the probability of the intersection. So running out of room, but this will be 1 minus probability of E plus probability of F minus, and here I'm going to make sure I put my parentheses, minus the probability of E intersect F, close brackets. So we're using the inclusion-exclusion principle plus the complement rule to figure this out. So let me write it out here. This will end up being 1 minus bracket probability of E plus probability of F minus probability of E intersect F. So the complement rule plus the inclusion-exclusion principle. So now this computation consists of only things that we know. So we just got to put all the numbers in. So that's 1 minus, and here I'm going to keep my parentheses, 0.5 plus 0.4 minus 0.1, all over, and we already did 1 minus 0.4, so that's 0.6. And so let's see, that's 0.5 plus 0.4, which is 0.9, minus 0.1 is 0.8. 1 minus 0.8 is 0.2. So that's 0.2 over 0.6, which is 1/3. Okay, so that last one's a bit of a doozy. We have to put together all of the theory that we've developed from chapter 5 up through chapter 6 to figure out this particular probability. But when in doubt, bust out the Venn diagrams and think about it graphically. It can really help you strategize your approach to a problem. Okay. So if that was tricky for you, study the problem, think about it, work your way through it. That's the only way you're going to really internalize these principles and the theory. All right. So one final problem for section 6.4. Here we've been given a table of a frequency table, and this is for a survey that was taken asking men and women what the highest degree that they achieved was. So either a bachelor's degree, a master's degree, or a doctorate degree. And we have the totals for all of these frequencies. Okay. And now we're going to be asked to compute a number of different probabilities using this frequency table. So first, what's the probability that if we select someone randomly from this group, sorry, that they'll have a master's? Okay. So in order to figure that out, I use the totals. So if we look at all these probabilities that we're computing, we have what I call simple probabilities and then conditional probabilities. So for the simple probabilities, we only ever use totals from columns and rows to compute them. So what's the total of number of people surveyed? It's 2,898. So that goes in the denominator. What are the total number of people with masters? That's 851. Okay. So punch that in the calculator. 851 divided by 2,898. And we get about 0.294. So we use the total in the master's column and the grand total for the simple probability. Okay, we're asked to compute another simple probability. Whenever we're doing a simple probability, we always use the grand total for our denominator. Then for the numerator, we just find the total of males. So of all the people surveyed, there were 1,201 males. Punch that into your calculator. 1201 divided by 2,898. And that gives us 0.414. All right. Now we're asked to compute a conditional probability. For conditional probabilities, we have to we use the given, the second piece of information here to help us eliminate numbers in our table that we don't need. So once I see this, I say we're looking at the probability that we will select a female given they have a master's. So the idea here is that we have 2,898 people that we have surveyed. We're going to sort those people so that all the people with the master's degrees are in one room by themselves. We're then going to walk into that room and grab a person at random. And the question is, what's the probability that when we walk into that room full of people with master's degrees, that we'll select a person at random that's female? So what is the grand total of people in the room? It's the grand total of people with master's degrees. So that's how many people are in the room. Of those people, how many of them are female? 522 of the people with masters are female. So that goes in the numerator. 522 divided by 851. That gives us 0.613. Okay, so same game again. Now we're computing the probability that if we pre-sort, we put all the females into a room by themselves, and then we walk into that room and we select someone at random, what's the likelihood that they have a doctor's degree? Okay, so how many people are in that room? It's all the females that we surveyed, which is 1,697. That's the grand total of women. How many of them had doctors? 93 out of the 1,697 had doctoral degrees. So we punch that into our calculator. And we get about 0.055. All right, so computing these probabilities with a table is quite a bit simpler than doing it using the formulas. So all that really matters is that you figure that the trickiest part is figuring out what the grand total is for the problem. So if you're doing a simple probability, it's the grand total is the denominator is the grand total of people surveyed. If you're doing a conditional probability, then the total that goes in the bottom is determined by the total for that particular category. So total masters, 851, total females, 1697. You can also see that, for instance, with this one, where we're computing our given as a masters, all of the numbers that we used came from the column, the masters column. We didn't use any of the other numbers in the table, just those in that column. And similarly for the probability where we're conditioning on female, all of the data that we're using, all the numbers that we're using to compute the probability is coming from the row, the female row here. Okay, so that concludes the review of chapter 6. I will post a review for chapter 7 on Wednesday, and the exam will be posted on Friday. Good luck.